This presentation is about our paper, Fast and Lightweight Online Person Search for Large-Scale Surveillance Systems. I'm from the Fraunhofer IOSB in Karlsruhe, Germany. My name is Lennart Moritz and I'm a co-author of this paper. We were tasked with designing an actually deployable person search system for the real world. It was to improve the usefulness of large-scale multi-camera surveillance systems, as manually doing person searches on this kind of data is a slow task. For our development and research, we had access to real city surveillance footage, and we had to fulfill requirements of supporting multi-camera networks, real-time processing, affordable hardware, and our system to be portable as well as extensible. Such a pipeline consists of a detection stage for person detection, the tracking, feature extraction for the detected persons, as well as storing these features and the actual person search in form of the retrieval task. In our work, we propose a collection of lightweight modules for person detection, tracking, and re-identification in real-world settings, and we prove their efficiency. We design and implement an online person search system and address challenges of real-world deployment for such a system and future systems to come. We also prove the real-time capability of our design and system and achieve up to 76 frames per second processing speed on affordable consumer hardware, so that we can offer a realistic baseline for real-world applications. To put our work into context, searching for a person of interest means finding all the occurrences of that person of interest in image or video footage. To do that, we use neural networks. We use ones for detecting persons and for generating features for them. We perform our person search on tracks of images of persons, not single images, to improve the performance and quality of our rankings. For the retrieval stage, which means the search, we calculate the distance between the features of a query image and our recorded database features to create a visual similarity ranking which can be interpreted by humans. There are a few things to consider when developing such a system for real-world deployment. For one, such a system needs to run on affordable hardware, as public safety agencies which might be interested in such a technology usually have limited financial resources. Also, to be able to react to an incident, we need to process our video in real time. Since the system is supposed to be deployed in changing domains and on unseen data, we need to prioritize re-identification accuracy in real-world conditions compared to on benchmark datasets for re-identification. Furthermore, users may want to add or remove cameras while the system is running without experiencing performance issues, so it needs to be scalable. Also, since we are touching upon the subject of personal data here, our system needs to comply with data protection laws. Many countries have laws for this. Often, only short-term storage of personal data is allowed. Here in Germany, where we develop, only up to 72 hours would be the legal limit. Now, on the right side, you can see a visualization of our system. It consists of multiple modules working together. We deploy these modules as Docker containers. We have modules for the single camera processing, the data storage, the privacy module, and the search module. For each of the camera streams that is present in our system, we deploy a copy of the single camera processing Docker container to process the input. This also has the biggest performance impact since the detection, tracking, and feature extraction is executed here. We use the single camera processing module to decode our incoming camera stream. We then apply the YOLO v4 person detector on each frame. We then create person tracks from these frames with the sort tracker or deep sort tracker. The benefit of the sort tracker, it is faster and uses less performance, but has no track recovery after occlusions compared to deep sort, which uses features to recover after occlusions. Therefore, we introduce our own track merging module, which can be used in combination with the sort tracker. That way, we keep tracks as pending if they are terminated and keep them open for future comparison of new beginning tracks, which we might then continue instead of opening a new one. In the end, we extract our features with OSNet, which seemed to be the best compromise between speed and generalization, looking at other networks that we have tested, and we train it using transfer learning on multiple data sets. In the data storage module, we store data for entire tracks, not only the images. We use a MySQL database to store metadata like the time where a track was captured or where exactly on the big images it was captured on, like the bounding boxes, as well as feature data. We also expect to integrate into an existing image data storage system from existing surveillance solutions. So for the image and video data, we use a network shared file system as a substitute. We need the image data to later visualize our search results, obviously. As mentioned earlier, the data storage module is checked with a privacy module, which frequently deletes outdated entries from that database and the file system. We use it to ensure compliance with the European Union's General Data Protection Regulation by enforcing maximum storage times, which is, like I said, up to 72 hours in Germany. To process incoming search requests from clients, we use the search module. These requests contain a query image and a time interval to be searched, but we also accept a watch list to be checked live. These images are then embedded into feature space with the re-identification CNNs to create a similarity ranking against the stored tracks, which is then returned to the clients. To calculate this ranking, we use Euclidean distance with normalized features, as it has been a fast way to create such a ranking. We run our evaluations on the multi-camera track auto dataset. We use two setups to test our pipeline. In setup 1, we use a GTX 1080 Ti graphics card, which is our weaker setup. In setup 2, we use a RTX 2080 Ti graphics card, which represents our better setup. We use the one-stage person detector YOLO V4 as it has favorable speed against two-stage detectors and showed superior accuracy against other one-stage detectors. In our tests, we tried using models in full and half precision and could not observe any differences between the detection accuracies while using them. The biggest predictor of computation speed was the input size for these networks, where you can see 3 different input sizes for the images with the speeds that we could calculate the detections for. The output of the detector is the input for our tracker. Here we compare the processing times of 3 variants of trackers. We use the sort tracker in combination with our track merging module, and the deep sort tracker. The deep sort tracker uses features of the detected persons to produce better tracks, but that costs a lot of computational time, which you can see affects setup 1 badly with up to 15 milliseconds on average per calculated frame. To select a right backbone network for our re-identification feature extractor, we evaluate generalizable re-identification performance by using leave one out cross-validations, meaning that we have 3 training and test splits and each dataset is used once during evaluation and otherwise during training. The datasets used were Market, Duke, and the Prey dataset. We trained using no augmentations and see that the OSNet outperforms MobileNet and ResNet by a large margin, which is why we decided to use it for generalizable re-identification. We then optimized this network using data augmentations. As we can see, there are a few augmentation strategies in the middle of this table. You can see that random dataset sampling had the biggest impact on the generalization improvements. And when we combine the most successful augmentation strategies and see if there's a difference between full precision and half precision models, you can see that we actually had better results using the half precision model. But since it significantly reduces processing times, we obviously went with that. When we combine these modules into our system, we can perform a qualitative analysis of a query image on the left with the 10 first ranking positions on the right. Within the ranking, we are ranking tracks of our real-world dataset, which we were able to use. As you can see, in our top 10 ranking, our person of interest occurs in 8 tracks out of these 10. And I can tell you that in the ground truth, the person of interest would have occurred in 9 sequences. So this marks a pretty good return. Let us now evaluate the real-time capability of the system. It is, in our experience, upwards of 35 frames per second that is required to be real-time capable for 30 FPS input streams. So you can see in the table, with a detector window size of 320 pixels, even setup 1 with the SAW tracker plus track merging module achieves 38.2 frames per second, which is real-time capable with balanced settings. With even better hardware, we can even use a deep SAW tracker or a improved detector window size. To conclude our findings, our system meets real-time requirements on affordable hardware with up to 76 frames per second processed, with balanced settings still exceeding 35 frames per second. Our system is applicable on unseen domains, which is tailored to the domain generalization challenge of re-identification and uncontrollable environments. We show a set of techniques and best practices in our paper for developing complete person search pipelines without overfitting to specific hardware or target domains, and show that our system is easy to deploy and easy to extend. If you would like to read more on our sources, please see these.